Hello, today we will continue from last time and take a look at the latest research trends in generative AI. Last time we looked at research on AI-based performance prediction. Since prediction is now possible, this time we'll try generation. How did we do generation again? It's about training a function that is designed to generate the desired x, based on g, within the latent space. We are going to look at the trends in generative AI research in the following 5 categories. The first topic we'll look at is generative design. First, I'd like to mention that in the industry, topology optimization is sometimes referred to as generative design, but topology optimization is actually just one type of generative design. What I will be introducing today can be described as generative design in its broadest sense. The concept of generative design has actually been used for a very long time. It has been widely utilized in the construction and architecture fields. If we look at the academic definition, it refers to any computational design methodology that can automatically explore new designs. So, the methodologies that were used in architecture have also been adopted in manufacturing, and generating various forms like these also falls under generative design. So, the ultimate goal of generative design is to explore a wide range of design options within a broad design space. As a result, it is usually used in the conceptual design stage to inspire people. Therefore, it's necessary to clarify the terminology once again. In the industry, many people refer to topology optimization as generative design, but topology optimization is just one of the methodologies within generative design. There is also parametric design, and there are generative models that use deep learning. Additionally, there are generative models using deep learning that incorporate all of these approaches together. There is generative design based on deep learning. First, in the case of topology optimization, its advantage is that it is a mechanics-based optimal design technique that can generate optimized topologies that designers may not have thought of. It can also take into account design constraints and manufacturing conditions, and since it is an optimization process, it guarantees engineering quality, which is another advantage. However, the downside is that because topology optimization is an optimal design process that does not utilize data, it inevitably takes a long time to complete the optimization. Because it does not utilize data, it does not take existing designs into account, so the resulting designs are not aesthetically pleasing. Also, the generated designs often resemble mesh-like structures, typical of topology optimization, which tend to look very similar to each other from a human perspective. Again, as I mentioned, data was not utilized. Next, parametric design is a method commonly used by designers. Based on certain rules or algorithms, you can quickly generate design proposals by simply changing the parameters without going through an optimization process. For example, in the case of a rectangle, the parameters would be the width and height. However, the downside is that the designer has to define the rules and algorithms themselves. Outside of the parameters defined by the designer, it is not possible to provide original or new designs. Next, in the case of generative AI models, they finally use sophisticated data-driven methodologies to generate brand new designs by utilizing vast amounts of historical data. And after the training process is complete, it is possible to generate designs in real time and can be easily used without specialized knowledge. However, the downside is that since these have been used mainly in the fields of deep learning and computer science, they do not reflect engineering design requirements or manufacturing conditions. And since the generation is done randomly, the quality of the designs cannot be guaranteed. Sometimes you get good designs, and other times you may get poor ones. It also requires a large amount of training data. Lastly, in the case of deep generative design, it refers to a form that effectively combines the advantages of data-driven deep learning and physics-based optimal design techniques. It enables rapid generation of design proposals while taking into account design constraints and manufacturing conditions. However, to use this technology, you need to have a balanced knowledge of both engineering domains and artificial intelligence. It requires a lot of experience and has a high level of development difficulty. So, although these technological changes are happening rapidly in academia, there are still not enough cases of industrial application, and there remain challenges to overcome for commercialization that can satisfy the needs of people in the industrial field. First, let's take a look at examples of topology optimization and parametric design. Parametric design takes the following form. For example, when generating a wheel, parameters such as the number of spokes or the size of the holes are set by a person through parameterization, and the design is created by modifying these parameters. Next, topology optimization is the methodology where you define the space you want to design, and by adding or removing material within that space, you can create a design with the highest possible stiffness. However, when you do this, you end up with a mesh-like design that feels a bit different from a wheel, as shown here. So, even with topology optimization, since it's still an optimization process, how can you generate a large number of designs? If that's the case, even without using data, you can use the following methods. For example, in the case of a TV stand, if you input the load conditions and boundary conditions, you can create a topology-optimized design like this. To create multiple designs, since this is an optimal design process, there are many local optima as shown here. For example, if you start from a different initial point, there's a chance you'll get a different design. And if you solve it as a multi-objective problem, you can extract various designs from the Pareto front. Lastly, there is a way to change the problem definition. For example, if you change the constraints related to manufacturing or processing methods, you could end up with a completely different design. However, in order to successfully address and overcome the various limitations that still exist today in parametric design and topology optimization, the field of engineering is currently and very actively engaged in researching generative design based on data. First of all, if you are looking to conduct comprehensive research in this specific area, there are three fundamental and critical factors that you must carefully consider. The specific methods of how to effectively represent the design, which particular generative model is best to use, and exactly in which domain it will be applied. So from this perspective, a variety of studies are being conducted. For example, the same design can be represented in various ways such as images, voxels, point clouds, meshes, signed distance functions, parametric forms, grammars, and graphs. And from the perspective of generative models, in the past, GAN and VA-based methodologies were the most actively used. Recently, diffusion models have been replacing almost all of these methodologies. Next, from a domain perspective, there are research groups working on topology optimization, groups researching materials, groups designing and generating 2D and 3D shapes, or even kinematics. These are the areas where such models are being utilized. However, if we talk about the biggest issue, it's that engineering design is usually done in 3D, but there is a significant lack of 3D data. For example, in fields like NLP or natural language, there is so much data available that massive models like ChatGPT can be developed these days. And in computer vision, it's very easy to obtain 2D images from the internet, so it's also easier to build large models. There is some 3D data available, but it's usually just small amounts for various classes like this. However, what is needed in the field of engineering design is a large amount of data for just a single class. Therefore, the 3D data used in computer science is not really suitable for use in engineering. So, if you look at the engineering field, there is some 3D data available, but the amount is significantly less compared to NLP and computer science. Nevertheless, one particularly significant and distinct advantage of the engineering field is that you can precisely calculate various aspects of engineering performance and subsequently generate comprehensive sets of data based on that. For example, these kinds of ideas have been used quite a lot. At first, you create a generative model using the datasets you have. After creating the model, in order to evaluate its quality, in computer science, people usually have to check it manually. But since we can run simulations, we use numerical simulation to determine whether a design is good or not. Only the designs confirmed to be good are selected again and updated in the dataset. And then we use that data to create a new generative model. By repeating this process iteratively, we can eventually create generative models that only produce good designs. Even when generating with GANs, you can train the model to generate data that exhibits strong engineering performance. And we also need to consider constraints. These could be engineering constraints or conditions related to the design space. In most typical scenarios, when using a SAGAN, you can incorporate the desired engineering constraints as specific conditions during the training process.